Okay, thank you. So, all right, so I'm going to continue my lecture series on p-adic approaches to rational points on curves. So last time I explained Chabauty's method, which is a p-adic method introduced in the 1940s for finding or bounding the number of rational points on curves. And so what I want to explain today, which is something I started last time, is how Min-Young Kim took Chabauty's argument and reinterpreted it in terms of just the curve and its homology. So the point is that there's no more in his reinterpretation. There's no more Jacobian, and the advantage of doing that is that enabled Kim to generalize it, where he could replace this sort of homology group, which is related to the abelianization of the fundamental group of the curve. He could replace it by deeper quotients of the fundamental group. All right, so I want to review what I started last time, which is this huge diagram, and so let me start by reminding you what the setup was. So K was a number field, and X is a nice curve, so smooth projective geometrical integral, and I fixed a prime of the number field where X has good reduction, and then P was defined to be the prime, the rational prime below that number field prime. Okay, well then you have this diagram. So I didn't explain everything in this diagram, so I want to go through the rest of the terms here and explain those. And one thing I did explain was this notation. So M hat was the p-adic completion of an abelian group M, which is just this inverse limit. And then if you want to get a QP vector space out of it, you can invert P, or equivalently tensor up to QP. All right. So the upper two rows are essentially Chabauty's argument. So I mean, this is the set we want to find, and the strategy for finding it was to understand these two images, the image of the Mordell-Weil group and the image of the local points on the curve, and because the rational points of X must lie in both. And instead of understanding them here, it was easier to apply the logarithm map, the p-adic logarithm, to enter this just a vector space here. And so the actual calculations are effectively done in here. All right, but this all uses the Jacobian, and so this diagram is supposed to replace this red box by this blue box, which doesn't involve the Jacobian. All right, so I already told you okay, you know what these things are. These are just the QP vector space associated to these, and so you get that part. So I think next I'll try to explain in more detail how you get V. All right, so first of all, if you have the p torsion of the Jacobian, that is a kind of homology. Well, so I'll write étale homology since I'm working over a field that's not the complex numbers. I mean, this is completely analogous to what happens over the complex numbers, where if you have a abelian variety over the complex numbers, and you want to know what the p torsion is, you can understand that analytically by taking the lattice, which is the homology over Z, and then taking 1 over p times the lattice mod the lattice, or equivalently the lattice mod p times the lattice, which is equivalent to what this is doing. That's the homology except tensor, over Z mod pz. So this is just the analog of this. And I mean, this thing you can define. I mean, if you're more comfortable with étale homology, then you can understand this as the dual. You can just define this as the dual. I mean, here there's not much question about what to do, because I mean all these things are just vector spaces. Okay, so yeah, and this also you can similarly, just as the étale homology is isomorphic to the étale homology, at least for H1, it's the same as H1 for the curve. You can similarly write this as h1 étal for the curve. And you can do, okay, and likewise, I mean, you can do the same thing not just for p torsion, but for p the n torsion. So you'll have the p the n torsion will be isomorphic to h1 étal x over algebraic closure, and then z mod p the nz. Okay, and then you can build the Tate module out of these. So okay, maybe I'll call this T. So this is the p-adic Tate module of the Jacobian. So this is, by definition, it's the inverse limit of j p the n with respect to the multiplication by p maps. And so this, well, you just take the same inverse limit here, and that's the definition of the homology. Oh, wait a second. I think I inverted something here. So, all right, sorry. Okay. I'm much more happy with cohomology than homology, so as you can see. Okay, so this is there. So yeah, Tate module is a kind of homology, and this is homology with ZP coefficients. All right, so yeah, and then finally, you can make the QP version by inverting P. So okay, so this is which is the same as T tensored up to QP, and so that's going to be, yeah. So this is the, by definition, this is what homology with QP coefficients means. All right, so yeah, and all these things have a Galois action on them, the action of the absolute Galois group of K. All right, so now, okay, so that takes care of, well, that tells you what V is, but now I want to explain the Selmer groups. So from those you get from the usual descent sequence or Kummer sequence. So if you have this exact sequence of viewed as a sequence of Galois modules, if you take k bar points, then from this one gets, well, the JFK mod PGFK injecting into the H1 K with values in here. And this is now Galois cohomology. This is different. All these things were étal cohomologies. This is now Galois cohomology. So, all right, and Selmer group of J, which is a subspace in here, and it's defined to be the, well, okay, I'll just write this for now. Classes that are locally in the image are locally in the image. So okay, I'll say what this is a little later. This is continuous cohomology, and finally you can invert P to get this inside H1 K comma V. All right, and all of these have their own Selmer groups that you can either, yeah, you can either build them up as you go along, or else you can define. All right, so this last one I'll call Selmer group of QP comma J of J. And yeah, and so yeah, and these are all called the Kummer. These maps are all called the Kummer maps. Okay, but yeah, and the way you can define the Selmer group directly in the last one is by using the Kummer map here. So H1 KV, and then do the same thing over the local field KV for each V. And so you have a similar similar Kummer map here. So H1 KV, comma V, and you can take all of them. You can take the product over V, and then you have restriction maps of Galois cohomology. And so if I give names to these two maps, let's call this one alpha and this one beta. Then you can define the Selmer group. You can define directly in terms of this diagram as the classes here. So it's supposed to be a subgroup up here. Of classes that are locally in the image. So meaning that when they're classes that map by under beta into the image of alpha. So it's beta inverse of the image of alpha. All right, and yeah, and the alternative way of doing it is to just build it up using the p-adic Selmer groups. So you take this inverse limit and then you invert p, and that's the same thing. All right, and oops, yeah, that should be the J. Okay. 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 So all right. So and just as with the usual Selmer group, maybe you know that, for example, if you take the P Selmer group, it fits into an exact sequence where we have this J of k mod P J of k injecting into this other finite dimensional group. So the P Selmer group, and then the error is measured by the P torsion in the Tate-Schaff average group. And so, well, guess what? The same thing happens here. So you get, there's an exact sequence that you can that measures how far this differs. I mean, this is what you want to know, and this is what you can get from computing the Selmer group. And the error is given by, well, it's given by sort of the Shaw version, the inverse limit Shaw version of this. So it's going to be the inverse limit of the p-adic part of torsion in Shaw, and then invert p. And then, well, I really want to write like another arrow here and then a 0, which should be there, but I mean, there's no room. Okay, so, all right, so yeah, all right, so maybe I'll just go down here, 0, all right. So, all right, so yeah, so that's an exact sequence, and actually this last term is itself supposed to be 0 because, well, if the p part of Shaw is finite, then this inverse limit is actually 0. So this should be 0. All right, so this is 0 if Shaw j p to the infinity is finite. Okay, so in other words, when you pass to this QP Selmer group, then this Selmer group should be measuring exactly what comes from the L-V group. All right, so now I've defined, okay, so I've defined this. And well, I guess I've also defined these things. So I've defined everything outside the blue box. All right. Now, unfortunately, the blue box is a little bit harder, but I will try to tell you something about it. All right, so. Okay, so. Okay, I mean, this is going to be, in order to define what's in the blue box, I have to tell you something about crystalline representations of the local Galois group. So, all right, so first, well, if you have a class of the local Galois group, a cohomology class of this absolute Galois group of the local field acting on V, so just by general things about group cohomology, this corresponds to an extension of Galois representations. So where you have, okay, so it's an extension of QP by V, and so the extension is E. So these are all fine-dimensional QP vector spaces with a continuous action of the Galois group of KV. And I mean, the way you go from one of these to a class is you can just take the H0 of this and take 1 in there, and that'll map to an element of H1 of this, and that's what the class is. Okay. Anyway, so you can think of these cohomology classes. You can think of them more concretely as being these extensions E. So as particular Galois representations. And then you can call this crystalline if, so, okay, this is a definition, but you're probably not going to be very happy about it because it just reads that this is, so crystal clear. It's crystal clear, yeah. So it's as crystal clear as this one is, yeah. So if you know what it means for a local Galois representation to be crystalline, well, then you know what this means for this to be crystalline. So actually, I think I will tell you this. I'll sort of tell you this maybe in the next lecture. But for now, just, OK, there's some notion. And it's something like an analog of being an unramified representation, except for p-adic representations. Unramified is not the right concept when you're looking at the p-tate module over a local field of residue characteristic P, then this is sort of the right notion. All right, so anyway, once you have that, then this F is a condition on it defining a subset of all of the entire group. Oh, did I switch? Sorry, I think oh yeah, no, this is fine. Okay, so V right now is, yeah, so maybe I should say, so V right now is going to be someplace above P. I mean, it doesn't have to be the curly P, but it's going to be one of those. Okay, so then you can define this to be just all the crystalline classes in the here. Okay, so that's some subgroup, some subspace. And then you can define this Bloch-Kato-Selmer group. So this is local, and now this is the global version. And so these are the classes in the global cohomology group, H1 KV, that are whose image in H1 in the local one is crystalline. And that should hold for every V dividing P. Okay, so, all right, so, okay, at least, well, I've sort of told you now what these things are. This is, and I think maybe I won't even try to define the rest of this, but yeah, if you can read. No, you don't. It turns out you don't need it. I mean, if you could try to put conditions, but they would already be automatically satisfied. It comes from the fact that that once you pass this pro-P version, those Galois groups. Well, it's almost if you look at a group over L, over a prime of L, then it's almost pro-L and so on. So you don't actually. So this is actually all you need. Okay. So what's the conclusion of all this? Yeah, by the way, if you want to know about what the Bloch-Kato logarithm map is, you can read about it. It's explained in the notes by David Corwin that I included in the abstract. If you go to Emmanuel Pear's the website for the semester, the one with the black background, then you can click on there and see and get links to all these these references. All right. So the conclusion of all this is that you get this simple, well, not simplified, but Jacobian free diagram. Okay. So which is this is the substitute for the top two rows of the original diagram, but this is Jacobian free. So all right. So and this map, I mean, in order to calculate the intersection of these images here, I mean, it's nice to have this map directly, and you can compute this. This is the thing that's computed in terms of p-adic integrals. So because this is essentially the same map as the map from here to here, which we defined by pulling back integrals here to integrals of one forms on the curve. If you remember that's what we did last time. Okay, so that's what it looks like. Yeah, and the point is there's no j. All right, so now how do you generalize this to the deeper quotients of the fundamental group? So okay, so first let me relate V to the fundamental group of the curve. So all right, so if you have the fundamental group, and we're always going to be talking about the étal fundamental group. So of the curve. Really, I should be writing some base point as well, but let me not worry too much about that. Okay, so there's always some implicit base point here. This you can think of, well, if you take the abelianization of this, the abelianization of pi1 should be the first homology, and so it's and that is what you get. You get. Let's see, I got to put the 1 in there. Okay, it's down here, I think. So yeah, for homology. So it is the étal homology. Except this is this is where you have all the p primary parts for all p, so it's like a z hat homology. It is like a profinite version of the classical thing over the complex numbers, where the abelianization of the pi1 is the h1, it's the h lower 1. But now we're interested for these purposes. We only care about the pro p part, and so you can project this onto the this is just a direct product over all the p's of these groups, and so you just project onto the p part, and then you can put, this is zp, this is homology, this is zp homology. That's like the tape module, and then you can embed that into the qp version. Yeah, and that's what we defined V to be, and I'll also want to think about this V as being it's a vector space over qp, but of dimension 2g, just like the tape module is rank 2g, and I want to think of this as the set of qp points of some algebraic group, which will be the 2gth power of the additive group. And this is not just a vector space, but it has a Galois action. It has an action of the absolute Galois group of K. Okay, so this is how you can reinterpret V in terms of the fundamental group. And now, and in terms of the abelianization is also, it's this pi1 étal xk bar modulo the commutator subgroup. That's how you get the abelianization, or the closure of the group generated by all the commutators. And so you can generalize this. This whole thing is the n equals 1 case of a more general thing. And what is that more general thing? It's, you again take the étal fundamental group, but instead of just quotienting by the commutator subgroup, which is like the second group in the lower central series, where the first group is a whole one, and the second one is this, if you quotient by the n plus first group in the lower central series. So now you'll get some, so now this is going to be some nonabelian group, some nonabelian quotient of the fundamental group. And then there's going to be some construction. Yeah, it goes along. It's a complicated construction. So, well, actually, it's not too bad. But anyway, there's some way to turn a profine group like this into an algebraic group whose QP points are this. So you get some higher analog of this V. I'll just call it V sub n, and it's going to be there'll be also some algebraic group, which I'll just for today I'll call curly V sub n. And so this thing here is some unipotent algebraic group. So it's really just some fine dimensional, nothing, just a fine dimensional algebraic group. Some group scheme of some group of fine type over the field QP. And well, just as this vector space had a GK action, this also has it has some GK action on it. Okay, so you have all that, and yeah, and now finally, what you can do then with all this is you can make a generalization of this diagram. So essentially, you just replace all the V's by V sub n, and so that's the final stage. Well, that's the final step of what Kim did. So he's generalizing. Okay, so you get Kim's diagram. So what does this look like? So again, you're trying to find the rational points of the curve by embedding it into the local points. But now you're going to map it to something that has more information than just the Jacobian did. It's this cohomology. Yeah, this is now just a set because Vn is non-abelian, and okay. But anyway, so you can define that, and then you have it maps to the local cohomology, and you have maps here, and then you can understand these by mapping to some. Well, okay. So there's something even worse than de Rham homology. There's the de Rham of a fundamental group. And then this is of the local field, and then there's some sort of nth quotient of this, and then it also has some filtration, some Hodge filtration that you can define, and get something like this. And these sets, I said these are sets, but they actually have a little more structure than just sets. These are actually equal to the QP points of some varieties. So maybe I'll just call this one. It's some higher version of this is what Kim calls a Selmer variety, and then this is also some point, I don't know what to call this, it's some local thing, so maybe I'll call it L for today. I don't think there's a standard notation for it. But so for this, and where this is for a morphism of varieties. Okay, I'm not explaining where this variety structure comes from, but it's actually, the varieties are not actually very complicated. I mean, the type of varieties they are, is not complicated. For example, when n equals 1, so when n equals 1, these are just vector spaces over QP. And then these two varieties are just affine spaces. And this is just a linear map of affine spaces. And in general, what happens, these are like iterated affine space bundles. Affine spaces over, affine bundles over, affine bundles over, affine bundles over affine space. Something like that. And this is some sort of, yeah. So these are not very, in that sense, they're not very complicated. And in fact, these things are all known. It's known what the dimension of these local ones are, because these are just, Yeah, because it's the same as this. It's just defined in terms that you can, I mean, we understand the fundamental group of curves well enough to understand what this looks like. But this is the hard thing. This is the thing that has the global information. This is the thing that's analogous to the Mordell-Weil group of the Jacobian. And so it's harder to figure out what that dimension is. Yeah?
Aren't they affine spaces as algebraic varieties?
Oh, that may be true.
It's just the canonical group structure.
Yeah, that's probably true, because I guess I think that's right. So yeah, okay, but yeah, the natural right. I think they as right. So it's even simpler. So they're really just affine spaces. But I mean, this map is not linear anymore. It's some. But
Kim told me that he for a while tried to make them into vector spaces because he knew they were affine spaces.
Oh.
And it was Mochizuki who actually helped him realize that they really couldn't be vector spaces.
Okay. Okay. Yeah. So I mean, they shouldn't be groups because they're nonabelian cohomology. So yeah. All right.
Just one point, because for the abelian quotient, you get a lower base point, but you can't ignore it for those higher quotients. So
Yeah. Right.
Below this, you need to assume that you have a k point.
Yeah. Okay. I said I was going to not mention base points, but yeah, that's true. But do you have something to say?
Maybe another very small technical point. When you take the quotient by the commutator subgroup, is this commutator subgroup always closed? Or
It's the closure. Commutator subgroup for a profile group means the closure of the group generic. Same for that's how you define the lower central series for a profile group. You always have to take closures. Yeah, subgroups in a profile group. If a subgroup is not closed, it doesn't deserve to be called a subgroup. So
I agree.
All right. Okay. All right. So the thing that one can say about this story is that now Kim proved an analog of Chabauty's theorem. So remember that Chabauty proved that if the Mordell-Weil rank was less than the genus, then the set of rational points is finite. And so the same thing happens here. So what Kim deduces from this, except that you need now some analog of that Chabauty inequality, and the analog is just that the dimension of the Selmer variety, which is that's playing the role of the rank. Then if this needs to be strictly less than the dimension of the thing it's embedded in. So if that inequality holds, that means you're going to get some functions on this space that vanish on this. And when you pull it back to the curve, you'll get some analytic functions. I should say that this map, just as that map over there was given by p-adic integrals, this map here is given by what are called p-adic iterated integrals. And so these are sort of concrete things. You start with a p-adic 1 form, you integrate it to get a function, the way we did in the last lecture, and then you multiply it by another 1 form. You get a new one. You get some sort of analytic 1 form. You can integrate it again, and so on and so on. So it's that kind of thing. So yeah. So you have these maps, and so if the dimensions work out the right way, then you get some functions here that pull back to analytic functions that must vanish on all the rational points. So the conclusion, yeah. So x of k will be contained in the set of zeros of some non-zero locally analytic function. So just given by some power series in each residue disk. So on x of kp, and so if that happens, then you know, because this is all happening inside a compact space, then the set of rational points is finite. And the reason this is better than Chabauty's theorem is that even if this fails for n equals 1, it might hold. In fact, Kim conjectures that it eventually must hold for a large enough n, but that's not known yet in general. Yeah.
It's good to mention that the fact that it's not zero is a very non-trivial theorem of Ken. And
Yeah.
it's related to the fact that that arrow
Right.
image is a closed analytic subspace, but is
It's Zariski dense. Right. It's the same thing that happened in the n equal 1 case. We needed to know that in the n equal 1 case, we need to know that any integral of a non-zero 1 form, or any was also a non-zero analytic function. So here it's not quite so clear because you have a combination of these more complicated things, but it's still true. So yeah, and that's something you can prove over the complex numbers if you want to, because it's the same, it's a purely formal thing. Yeah.
So you mentioned that we understand the dimension of Ln. Is it just some formula in n in the genus?
Yeah,
Yeah.
it's just some formula in terms of, yeah, it's just some, yeah. Okay, any other questions? Okay, so I think we'll now, at this point, so this is the end of what I was going to say about Chabauty's method and nonabelian Chabauty. So what I want to do now is move on to the Lawrence Venkatesh paper, and there are going to be a lot of preliminaries for that. And so, okay, so this is a complete break right now. And not only is it a break in the sub-break, but I think we'll actually take like a 3-minute break, if that's okay, or just so I can erase the board. Or you can film me erasing the board. But if anybody wants to go out, you know, whatever, and come back in 3 minutes, that's okay, because I got a lot of boards to erase. So let me start by discussing Faltings' finiteness theorem. This is not the finiteness theorem for rational points. This is the finiteness theorem for Galois representations, or for semi-simple Galois representations. This is one of the lemmas that Faltings proved in his paper on the Mordell conjecture that was needed as one of the ingredients. And Lawrence and Venkatesh also need this. So it's not completely independent of Faltings' proof, but it uses sort of the easier parts of Faltings' proof. All right, so K is always going to be a number field. And S is a finite set of places. And just for simplicity, let me just assume that it always contains all the Archimedean places. And okay, so there's a classical theorem of Hermite, which is that if you have, okay, so if you fix K and you fix S and you also fix a positive integer D, then if you look at all the degree D extensions of K that are unramified outside S, then, okay, up to isomorphism, then that's fine. There are only finitely many degree D extensions that are unramified outside S. Okay, so that's one of the ingredients. Actually, so this theorem is actually not very technical in terms of the ingredients that I use. I mean, this is not a very hard theorem. I mean, you probably saw this in your number theory class. So that's one thing. And the only other thing you really need is the Cheprov density theorem. And so for this, let me just introduce a little more notation. So for each non-Archimedean place V, you have well, inside the Galois group, for each of you get well, you can define a Frobenius element, and you can also define an inertia subgroup. So I mean, technically speaking, if you want to talk about the inertia subgroup, you have to choose. You have to extend the valuation V up to K bar. But so I'll just assume that's done for each V once and for all. Oh, it's not uniquely defined.
But still.
Okay, yeah, I guess for, well, I mean, you can just.
Takes a quotient.
I mean, you just take any element that.
It's not one. You're not presumably going to take traces, so you just say.
Yeah, I'm only going to use them for unramified V in the end. But yeah, okay, if you want to, you can assume that V is well, except these I don't. Okay. Yeah, so it's not going to matter. It's not. I mean, you can always choose some element. And okay, so it's associated to an extension of V to K bar. Yeah, all right, and then so if I have a homomorphism from this absolute Galois group to some other group H, so this is H is just, I don't know, some group. So then I'll call this unramified outside S. That means that the image, that all the inertia groups are mapped to 1. So that should be hold. That should hold for all V outside S. Okay, so that's the definition. And now I can state a weak version of the Chebyshev density theorem. So, all right, so I don't think anybody else calls it this, but I'm going to call it this. Weak. So, okay, so given K and given S and given a continuous homomorphism from H, sorry, H is a continuous homomorphism from the absolute Galois group to some finite group, and finite means, okay, finite end. So this is some discrete finite group. Okay, so the kernel is finite, is the finite index. And okay, and this should be and this is unramified outside S. Given all that, there exists a finite set T of places of K, and this disjoint from S. So these are all unramified primes. Such that if you take the Frobenius elements for just these finitely many Frobenius elements, just the ones associated to the places in T, then those are already enough to cover the image of H. So the image of those finally, that's the same as the whole image. I mean, this is not so hard to do because the image is finite, so there are only finitely many things you have to cover. But I'm just saying that, yeah, you can find, all this is really saying you can find one Frobenius element that maps to each Galois. I mean, each element there. So, I mean, Chebyshev density theorem tells you a lot more. That tells you there are infinitely many map, and not only infinitely many, but actually a positive density that cover each element. But only one is one. So, all right. And now there's also, well, something I'll call uniform weak Chebotarev, which is, it's almost the same statement. There's just a subtle shift in the order of quantifiers. So, all right. So given K and S and they're equal to 1, there exists a finite set, finite T disjoint from S, such that now for any H, for any group H, finite group of order less than n, and any homomorphism from GK to this H, unramified outside S, same conclusion holds. So H, that the Frobenius elements from this finite set cover the whole image of H. Yeah, so the difference is that now I have to choose the T in advance before I know what the homomorphism is. But of course this follows immediately from the previous one, because I mean it's not hard to find a T that works for all the little h's, because there are only finitely many little h's by Hermite. So there exists only finitely many H up to isomorphism. So okay, so all right, so that's So those are the ingredients from number theory that are going to be used in Faltings thing. And one other lemma that I'll state here. So this is about lattices in Galois representations. So if you have a finite dimensional QL representation of a, let's say V of the absolute Galois group, and this contains a GK stable lattice. So, but let's say I mean a ZL lattice. By lattice, I mean a ZL submodule that spans the whole thing. So a ZL lattice. So okay. So by that I mean a ZL submodule of V. So let's say L, such that it spans the whole V. That's what that means. Okay. Is this familiar to people, or should I? How many people want to see a proof of this?
I believe it's the very first assertions that prove themselves of my analytic representation.
Okay, that doesn't surprise me. Okay. Anybody want to see the proof? Yes? Okay. All right, I'll just do it quickly. So proof is, all right, so start with any lattice. I mean, it's easy to find one lattice. I mean, this is just a finite dimensional vector space, so you can just choose some ZL module of the right rank, any lattice, and then move it around by the group. So you move it around by each group element. So you take this for all G in the group, and then you just take the span of all of those, the ZL span of these, and so this gives you, well, it gives you some ZL submodule, but and it's obviously stable now. So L is, it's obviously Galois stable because when you hit it by an element of the Galois group, it just permutes those. And it's also obvious that this spans the whole vector space, because even L0 by itself spans the vector space. So the only thing that's not so clear is whether L is finally generated, whether it's going to be oh, sorry, I think I forgot to say here. It should be a finally generated, yeah, or free if you want. ZL submodule. So you're not allowed to take the lattice to be the whole thing. Yeah. So, okay. All right. So yeah. So the only thing to prove is that it's finally generated, but that you get by using the compactness of the Galois group. So, because if you look at with the action map of the Galois group acting on V, the image of GK cross L0 is going to be compact, because GK is compact and L0 is compact. And so, hence this image is contained in some finely generated submodule of ZL submodule of let's say of this V. Okay, but I mean a finely generated submodule. Oh yeah, and then L is the span of the span of this image. So L is contained in M. So L is going to be finally generated too. Okay, all right. So that proves that lemma. So now it's time for the main lemma of Faltings thing. So now given Ks a prime L and a positive integer D, there exists a finite set of places T disjoint from S, such that if you have two Galois representations, if rho and rho prime let's say they're d-dimensional QL representation. So it's the Galois group acting on a QL, find a d-dimensional QL vector space of the absolute Galois group, and they're unramified outside S. Well, the conclusion is going to be, okay, there's going to be a missing line here, but the conclusion is supposed to be that they have the same character, that the traces of the representation are the same. So that the traces, let's see, traces of, oh, I guess I could say, yeah, the trace of, the Frobenius elements are dense. So actually, let me maybe just say that the trace of G equals trace of, well, okay, let me just say it in terms of Frobenius. So Frobenius is equal to the trace of rho prime of Frobenius V for all, okay, I keep changing my mind so whether I want to do this for all G. Okay, so let's do it for all G. I'll say something. I haven't finished. There's a missing line here. So wait. Okay. So let's wait until for all G in the Galois group. And here I want to say such that what I get to know is that the Frobenius elements for the finely many places in T are enough. So if I know that the Frobenius elements in T have the same trace under the two representations, then actually all elements of the Galois group are enough. So it's enough to, yeah. So the whole representation, at least their traces, are controlled by just finely many elements. That's yeah. And notice that, yeah, it's very uniform, and that this finite set doesn't even depend on what the representation. I mean, you don't have to know the representations in advance. All you need to know is that they're d-dimensional and unramified outside S. Okay, are you satisfied? Okay. Okay. So, all right. So this proof is a little bit. I mean, there's nothing very technical in it, but it's a little bit subtle. So. So no, I got it wrong several times as I was preparing, so hopefully this time it's right. So it's a lot of details. Okay, so let T be as in the uniform Cherebrov density theorem. That statement I had over there. And for the number n, I'll define n to be L to the 2d squared. Okay, it'll become clear why I want such a big n later. Okay, so now I get to know that this conclusion holds for homomorphisms to groups of order less than that. Okay, so all right. So and I mean I'm trying to prove the statement. So let me give myself the two representations. So rho and rho prime. So let's say they are d-dimensional representations. So they're QL representations, and they're unramified outside. So just as in the hypothesis here, so unramified outside S. And okay, such that exactly as there, such that the traces agree on the Frobenius elements coming from T. So this holds. So that holds for all V and T. Okay, and I somehow want to show the traces are equal on all Galois elements. Okay, so first of all, without loss of generality, by this last lemma I proved about the lattices, I can assume that rho and rho prime, I mean, they don't just take values in GLD of QL, but they actually take values in GLD of ZL, because I just choose a basis for each one that's associated to this Galois invariant lattice. And then, yeah, then the matrices will all be in GL2 ZL. OK. OK, so now the clever idea is to define inside of the direct product of two copies of the d by d matrices over ZL, define a submodule, the ZL submodule spanned by the images of the two representations. So for each element G, you get a pair of matrices in here. And you take those things for all elements of the Galois group, and you take the span, the ZL span of those. And well, you can see that I mean, if you multiply two of these, you get another one. So this ZL submodule is actually an algebra. It's a ZL because it's going to be closed under. It's a span of things that are closed under multiplication. So it's a subalgebra of this product of matrix algebras. OK. All right. So far so good. And now let me define a homomorphism. So let H be the composition, the following composition, where I have the Galois group mapping into the units of R, which is that's just the obvious homomorphism where each element G goes to this pair. So yeah, so let me write. Maybe I'll write it. So it's rho comma rho prime. So it sends each element G to this pair, and then from there you can go on to R. I mean, R is a ZL module, so I can take R mod LR, take the unit group of that. And OK, so that's the definition of H. And then for each V and T, for each V and T, I have a Frobenius element here. And let me just give names to the images. So the image in here I'll define to be R sub V. And the image in here I'll call R sub V comma L. OK? So that's. And notice that last group, R mod LR, that's a finite group because, well, R is a finite rank ZL module. So R mod LR is going to be finite dimensional FL vector space. So, well, OK, maybe. All right. So, OK. So I want to make a bunch of claims. So the first claim is, yeah, not only is it finite, but I can actually give you an upper bound for its order. In fact, it's going to be less than or equal to n, which is good because, well, I mean, that's why I chose n that way. So. All right, so yeah, so first of all, yeah, so as a ZL module, I mean, what does R look like? So, I mean, R is going to be, it's a torsion-free, hence free. It's free of rank. Well, I mean, what the largest rank could be is the rank of this, which is d squared plus d squared. And so, OK. OK, so if you want now, so if you want to know the order of this group now, it's going to be less than or equal to the order of this ring. But R is free of rank less than or equal to that, so this is less than or equal to L to that, which is that. Yeah. OK, that was so. And the next claim is that this homomorphism H is unramified outside S. And, well, this is kind of obvious because, well, by assumption, this rho prime homomorphism is unramified. So that already in the first step of that composition, the inertia groups are getting killed. So outside S. Okay. So the third thing I want to claim is that if I take all these images of just the ones that come from T, just the images of the Frobenius elements from T, then this is already enough to cover the entire image of the Gall group of this homomorphism. And yeah, and not only that, but I want to say also that this image is large enough that it spans the whole ring, this as an FL vector space. So okay, so I'm making two claims here. So well, okay, so for the first one, okay, so let's see. So the proof here, so the proof of this one is just, well, it's just 1 plus 2 plus the uniform weak Cheryshev density theorem. Because I mean, 1 and 2 check the hypotheses that you need. You have the target group is small enough, and also it's unramified outside S. So by the conclusion, which I was careful not to erase quite, well, I didn't erase it yet, it tells you that the Frobenius elements are enough to cover the image. So yeah, so that's that part. And as for this other part, how about the spanning part? How do you know that's true? Well, for that one, you can just say that if you just look at the first step of that homomorphism, of that composition, just from here to here, that image is, this spans R as a ZL module. Because R was defined, well, R was defined as the span of of those images. So yeah, if this image spans R as Z module, then you just push everything forward to R mod LR, and it'll span it as an FL vector, as a FL vector space. Okay, so that takes care of that. And so okay, so the final claim here is that now. So okay, so these were the final images here. But if I look at just the step just before it, if I take the elements of R that come from T, that come from the Frobenius elements of T, then I want to claim those. The set of those spans R as a ZL module. And so the proof of that is just, well, you know that they span it mod L, and so you just apply Nakayama's lemma. Okay, so in other words, these elements, these R, V's coming from Frobenius elements in T, they tell you a lot about, they generate R as a, so now what you can say by hypothesis on these two representations, I mean, they have the same traces on the elements, on the Frobenius elements from T. So that tells you that in other words, each of these RVs that come from the Frobenius elements in T, each of those has the property that if you take its two projections, so if the two projections, I mean, there are two ways to project from R onto this matrix ring, and the claim is that those two things, they have the same trace. This is just a restating of this hypothesis. So, well, that's good news, because now since these RVs span R, you get that, I mean, just by linearity, you get that every element of R has the same every element of R has this property, has this property. So the property that its two projections have the same trace. And so finally, you can, so in particular, for any G in the Galois group, you get that you can apply this to say that rho of G and rho prime of G, that this element of R has this property, which is just saying that they have the same trace, which is what we're supposed to prove. Yeah. Yeah. So that's it. So that takes care of the main lemma. So the rest are just now corollaries of this. So so the first corollary is just, well, it's essentially the same theorem, the same lemma here, except what happens if you also know that the two representations are semi-simple? So in other words, they're direct sums of irreducible representations. So if I add the word, all right, so now I guess this is now a corollary. Yeah, sorry for people taking notes, but let's see. So if I just put in the word semi-simple here, then I can, well, I get this conclusion, but now this has an extra consequence that I can say something better than this. Not only do they have the same trace, not only do they have the same character, but then they're actually isomorphic, equivalent representations. And the proof of the corollary is just that, well, I mean, if you're over a characteristic zero field, if you're talking about representations over a characteristic field, such as, for example, well, how about QL? So then a semi-simple representation is determined by its trace. So by its trace. Okay, so that's this. Okay, so now I can state the final form of Faltings' fineness theorem. So this is what this is the only thing we're gonna need to remember going forward. So we're gonna fix K, fix S, fix L. So that's the L for the QL for the representations, and then fix D at least one, and for each place outside S. So there are infinitely many of these, but let's just fix some finite subset. Be a finite subset of QL. So then, if you take the set of semi-simple Galois representations, d-dimensional QL representations of this global Galois group, unramified outside S, outside S, such that the trace it belongs to this prescribed subset for all V not in S. Okay, this is supposed to be. Okay, then that set of representations is finite. Oh yeah, up to equivalence, of course, up to isomorphism. Yeah. So the proof of this, well, there's not much to say. I mean, once you know. So the proof is you find T, you use the main corollary So you find T. And then you have this set of representations that we're talking about. It's going to inject just into the product. I mean, this says that the representation is determined by its traces at the elements of T. So you can just put in here the product of the V's in T. And so you get the set of representation injecting to some finite set. So this is finite. Yeah, the way this is going to get used is there are going to be situations where you know something about the traces of representations. So if these are representations coming from a tall cohomology of some smooth projective varieties, then the Weil conjectures tell you, they constrain the possibilities for the eigenvalues of variance. You know they're whatever, algebraic integers of absolute values such and such. And so only that gives you this fine set of possibilities. And so that's going to be used here. Okay. Any questions about this? So that's this is one of the main ingredients. So okay, now you can forget everything except for this theorem. All right? And maybe it'll take another 2 minutes to erase everything else. We're almost done, but what?
We won't do a break, but you can erase.
Okay, yeah, you can do what you want. Okay, so I still have some other ingredients I have to talk about, and I won't finish them all today, but well, we still have after this. We still have 2 more lectures, so. Yeah?
You know the source of the effectivity Faltings theorem is somewhere around this step. It's either this or something like, if you know you're given the representation, how do you construct a new variety in that isogeny class that's defined over the field.
Mm-hmm.
Is this the step? Like,
I don't remember exactly. I think is there only one place? I thought there was maybe more than one place. But anyway, I think this is a problem because
like how do you,
if you
I don't know that much about Gauss representation, but this is sort of asking if you give me a finite set of potential traces.
you want to know whether you can make this effective. Like if I give you the K, S, and L, and D, can you somehow describe this set of representations?
You give me an injection to
I've sort of bounded it by some finite set, but I haven't. Yeah, I don't know. It's not obvious to me that this is effective. So
okay, that's fine.
I don't know. Does anybody else have a comment about this?
Once you can produce an abelian variety that's defined over your field in an isogeny class, then you're in a position.
Yeah, but there might be some things where you don't know whether it comes from.
Yeah, I mean,
Abelian variety.
it's
Yeah, I think that might be hard. I don't know. Yeah, Hermite's theorem is certainly effective, and yeah, I guess Chebyshev is also effective. So that all those things are effective, but here we're just giving an upper bound for this set of representations, and yeah, it's not clear which of those tuples in ZV are actually realizable by a representation. So I think so.
But you can bound the degree of the isogeny.
Yeah, that's.
It's like Maser-Wurzel.
If you know the height of the if you're given the abelian variety, yeah, then you can do it. But yeah, okay. All right, so what I want to do, I'm not sure if I'll have time. I'll say a lot more about this later, but I need to review all the cohomology theories. So for the unfortunate, well, not all of them, but a lot of the major ones. I mean, because Lawrence and Venkatesh actually use all these 4 different cohomology theories in the proof and the comparisons between them. So I want to review all these things. So but I don't want to do it in the middle of the proof because there's going to be enough other complications coming in. So I just wanted to review all these. And I'll just do it for smooth projective varieties. So no compact supports or whatever, just smooth projective or smooth proper varieties, say, over K. So okay, so I have my X, and what can I do? I can, so maybe most classically, if your field happens to be the complex numbers, then you can take the singular cohomology or p-adic cohomology. I don't know, maybe I'll put a B there for that. Okay, so you just take the manifold of complex points with the analytic topology, and you take the singular cohomology of that topological space, and that gives you some, yeah, that's some finely generated Z module, finely generated abelian group. Okay, and a related thing you can do, if you choose, in general, if you choose a prime that's not equal to the characteristic, then you can define the Italic cohomology. Let me just do this with, and you want it for the geometric object, so you base change to K bar, and, or well, I guess K separable. Okay, I'll just write K bar, but anyway. So, and then for this you can take, well, you can take Z mod LZ coefficients, but let me just do Z. I can pass to the inverse limit and take ZL coefficients. And so this, what kind of object is this? This is a finely generated ZL module. But it's better than that because it also has because X is over K and this is over K bar, you have also a Galois action, a continuous action of the absolute Galois group of K. All right, so a third thing you can do is over any K, you can take the algebraic de Rham cohomology of X. So I mean, if you want to do this algebraically, you have to use hypercohomology. So anyway, I don't worry too much about this. But you take the de Rham complex, the algebraic de Rham complex, and take its hypercohomology. And okay, so what is this? So this is well, it is a finite dimensional vector space, but also it's filtered. So it's a filtered finite dimensional K vector space. So filtered means that it comes with a, so yeah, it comes with the Hodge filtration. So which is a descending filtration. So it means that you have a descending sequence of subspaces. So it starts with fill 0, which is the whole space, and then yeah, so that's the whole thing. That's the big vector space, and then that contains the fill 1 of this, and so on, and eventually gets down to 0. Okay, so. All right, I didn't have room for my fourth one. Oh, I'll just go way around here. Okay. So this last one is going to be work if. Let's see. So if K is perfect of characteristic P. I could just take de Rham cohomology, but that would just give me a vector space over this characteristic P field. And if I want to compare it to the others, I'd rather have cohomology taking values in a characteristic 0 field. Well, I guess I could also get that from the Italic cohomology. But there's another thing you can do, which is to take the crystalline cohomology. Yeah, and again, this is complicated enough that I'm not going to give the full definition. It is the cohomology on a sheaf cohomology on some site attached to the variety. But I'm not going to tell you what that I'm not going to tell you what that site is. But anyway, I'll just tell you the kind of object that you get out of this. So, right, there's always a question about whether you write an I here or a Y. But I guess since we're in France, I guess I'll write an I. So, All right, so this is maybe the notation I'll use is this. So here, I'm just using the notation that W is the ring of Witt vectors of this characteristic P field, of this perfect field, and yeah, so this is the ring of Witt vectors. So if you don't know what Witt vectors are, just think about the case where K is FP, and then this Witt vector ring is just ZP. In general, it's just a complete discrete valuation ring whose residue field. It's a characteristic 0 thing, DVR, whose residue field is K. All right, so yeah, and this thing also has this Witt ring also has a Frobenius, which is not raising to the pth power, but it's more like a Galois automorphism. So if K were okay, anyway. So you have that ring automorphism, and then this thing, the type of object that the crystalline cohomology is it's a finitely generated W module. But again, it's a little more than that. It comes with a semi-linear operator phi, mapping this to itself. So okay, so maybe I should put that in here somewhere. So there's a phi acting as a map from this to itself. And okay, so semi-linear means this means that it satisfies. I mean, if we're a linear map, then when you multiplied an input vector by a scalar, it would just come out as this. But if semi-linear means that when the scalar comes out with a twist, so it's twisted by this Frobenius operation. So this is supposed to hold for all. This condition means that this holds for all scalars and for all the vectors. Yeah, and okay, so yeah, and this phi is also called Frobenius. It's like it comes from the absolute Frobenius morphism of X, and that induces by pullback. It induces this operator on this cohomology.
If K is FP, is F on the Witt vector just raising to the pth power?
Yeah. So if K is FP, then this F is actually just trivial. It's just the yeah. So and if K is like FP squared, then this would be like the Galois automorphism of the degree 2 unramified extension over QP. So that's, yeah. Okay, so, all right, so, yeah, but this phi could, even if K is FP, this phi could be non-trivial. This is, okay. because the absolute Frobenius morphism on X is not trivial. Okay, so, I think I'll stop here. So what I'm going to have to do next is to relate these 4 different cohomology theories. So there are various comparison theorems between them, and we're going to need many of them in order to do what we need to do. So all right, so stop here. Yeah. So see you next week.